It would be nice for you to draw this. Let's come quickly to light wave. Now, we know definitely that light has a number of sources. They could be man-made lights, which include candles, light from electric bulbs, and the natural light we have in the solar system is the sun, the stars, even glowworms. Now, we can group them into luminous and non-luminous sources. When we say they are luminous bodies, that means they can generate and emit light by themselves. Example is the sun, the stars. But we have non-luminous objects or bodies. This one, they depend on man-made sources or they depend on natural sources. An example is the moon. The moon, it does not have the light of, does not have a light of its own. Rather, it positions itself close to the sun and reflects the light from the sun. Okay. Now, light is an example of electromagnetic wave. Why? It does not require a medium to travel. We know definitely that there are three different types of medium. Number one, we have the transparent medium. Now, these are materials that allows light to pass through them. Sorry, I am just talking. I hope you are taking note of these things I'm saying.
Yes.
Okay. Now, we have the transparent medium. Now, the transparent medium, these are mediums, these are materials that do not allow, or sorry, that allow light to pass through them. Examples are glass, we have water. They allow light to pass through them. But we have some bodies that allow little light or small amount of light to pass through them. For example, your Polaroid glasses, frosted glass, the tinted glass is an example. They allow just little light to pass through them. An example of such is, oh sorry, I just told you they are tinted glasses, the frosted glasses, and those kind of materials are called translucent. I've talked about transparent, and I said we also have translucent materials. These translucent materials allow little amount of light to pass through them. Now, the last one which we have, they do not allow light at all to pass through them. An example, I mean, they do not allow light to pass through them, and we have them as opaque objects. They are called opaque materials. They do not allow light at all to pass through them. Example is the wood. Example is the wood. Okay. Now, which I want you to also write this, that the direction or path which light energy travels is called the ray of light. The direction or path along which light energy travels is called a ray of light. It's called a ray of light. For example, when we have the direction through travel is called a ray of light. But when we have different collections, sorry, you don't mind my rays, different collections of rays are called beam. Please write that. Collection of rays, collection of light rays is called a beam. All right. Now, please write this. Now let's look at types of beam. BEAM. There are three types of beam. Number one, we have the parallel beam. Parallel beam. Number two, we have the convergence beam. and we have the divergence beam. Okay, now the one I showed you here, this is the parallel beam. But when we say convergence, that means they all come to a point. Convergence beam, they all flow to a point. And what do we mean by divergence beam? That means, remember, the convergence beam, they all come to a point. But when we talk about divergence beam, from a point, they are going out. Look at their direction. The direction is very important. Their direction is very, that means they are coming out from a point. They are coming out from a point. Okay, divergence beam. So we have a convergence beam, parallel beam, and divergence beam. Okay. Now, for parallel beam, the rays are parallel to each other. For example, um, for now, please write this parallel beam. The rays are parallel to each other. Can you give me an example of such kind of beam? Hello?
Yeah.
Okay. Now, okay, an example of such is your set. Do you know what they call searchlight? Rechargeable lamp.
No.
Rechargeable.
Okay.
Can you remember that?
Yeah.
Okay. The beam from a searchlight or from a rechargeable lamp, we call them the parallel beam. Now, but if the beam meets at the point, converge at the point, they are called convergent beam. But if the beam spread out or appear to have originated from a source, we call them the divergence beam. That means they spread out from a source. For example, the torchlight. The torchlight spreads out from a source. Okay. Now, I want us to note this, that light travels in a straight line. And that is what we call rectilinear propagation of light. Okay, light travels in a straight line. And when you get to school, I believe you guys will be doing what we call um, experiments to demonstrate rectilinear propagation of light. That means that light traveling in a straight line, you're going to be using a ray box. You're going to be using a ray box. Now, what's a ray box? Let me see if I could see that online. Remember, I said that when light travels in a straight line, we call that rectilinear propagation of light. Now, rectilinear propagation of light means that light is traveling in a straight line. But what are the evidences to prove to us that light travels in a straight line? Number one, formation of shadows. Formation of shadows. Now, when light rays from a source fall on an opaque object, you notice that what? A shadow is being cast. Have you ever noticed that your shadows most times are bigger than you?
Yes.
Oh, good. I believe when you were much more younger than this, if it was dark in your house and oh, you didn't use lantern, come on, you missed out in that stage. I guess the first time I saw that, we're using lantern then, and I just saw we used lantern. So because human bodies are opaque to an extent, that's depending on the kind of light that passes through you. Oh God, I saw my shadow. God, I was damn scared of that. So later I got to realize, come on, why is this thing pursuing me now? Why is it following me? I later got to understand that wow, that's true. Light travels. That's just to show that light travels in a straight line, because we are opaque. So when light is cast, or when light falls on an opaque object, shadows are formed. Now, this proves to us so much that light travels in a straight line. Oh, my download is complete. So let's see if we can watch that.
Raybox is an outstanding model which
Okay. Thank you. Okay.
every school should have in their laboratory. Let us see how we can use it and how to make it.
Are you serious? How to make
It
it?
works on
Come
AC
on.
current, so it is very convenient to use. Use the card.
Okay. I'm not interested in how to make it, but this is it. You can make it if you want to do, but this is how it is. There's a light shining inside. You kept okay. Let's watch this first.
Cardboard slits to produce one ray. Cover the box from the top and switch off the light. You can see that light travels in a straight line.
So did you see that? This shows that light travels in a straight line. Did you see this?
Yes.
Did you see this? Wow, awesome. Light traveling in a straight line. Awesome. Okay.
When you place a prism, you can see the incident, refracted, and emergent rays.
Did okay? Are you seeing that it's reflected and
Yes.
there is refraction, bending? Now we are looking at the properties. Look at this bending of light here. Look at where it bends here. It bends from here and bends to this place, and there's a reflection here. So we have light traveling in a straight line, the refraction, the reflection. Okay, all right, this is awesome. This is awesome.
You can clearly see the bending, which is called refraction of light. When you place a white screen, you can see the dispersion of light, that is spectrum of 7 colors.
Okay, have you heard of dispersion of light before?
Yes.
Okay, what is dispersion of light? Dispersion of light is actually the separation of white light into its component colors. Can you write that, please? Dispersion of light is actually the separation of light into its component colors. That means the colors of a rainbow. The separation of light the separation of light into its component colors. The separation of light into its component color, that is called dispersion. You can, if you notice very well, you just discovered that this light has been separated. Hello, are you there?
Yes.
Okay, this light has been separated into component colors. That means we have them as red, orange, yellow, green, blue, indigo, and violet. These are the colors that it separates into. Roy GB, Roy GB. It's separated into Roy GB. So white light will be separated into those component colors, and whenever it separates into those component colors, that is called dispersion. All right, did you get that, please?
Yes.
Okay, let's continue.
Be more innovative and place a plane mirror in place of the screen. See the brightness of the colors. I am sure you have not seen it before, like this. You can also do the Newton's experiment of recombination of the spectrum. Place another identical prism in opposite direction and you will see the 7 colors recombine, and again you will get white light.
Okay, did you see that? Also, let me explain what just happened. Normally, when light passes through a prism, there is what we call dispersion. That's the separation into its component colors. And when these component colors passes through a prism again, it gives you what you call a white light. This proves to you that when you see a light that is white, a white light, it consists of the 7 colors. Why? Because when it's separated into the 7 colors, using this first prism, it's separated into 7 colors. Now, all the 7 colors will now pass through this other second prism. And now what we have here is the white light. So this proves to us that light travels in a straight line, number one, and then white light consists of 7 colors. Do you understand that explanation, please?
Yes.
Hello? Okay, thank you.
Yes, sir.
I still not able to understand why most of our teachers still using old boring method of teaching ray diagrams by drawing it on the board. In spite of these innovative devices, you can verify the law of refraction using plane mirror. You can see the clarity in darkness. And be innovative and try to make different shapes using different mirrors. I am using 3 mirrors to make a triangle. From that one emergent ray. You can produce parallel rays by using ray box. You can see the reflected rays bends towards the center when it is reflected by a concave mirror. You can also see the focus. Where the two reflected rays intersect each other. See how the reflected rays moves away when reflected by a convex mirror.
Okay, we'll get to understand this when we start talking about convex and concave mirror. Oh, I started off by saying retina propagation of light, that when light rays, okay, okay, let's come back here. Okay, that when light rays falls on an opaque object, what we get is a shadow. All right. Um, coming. That means when we have now when we have light rays coming up on these opaque objects, for example. Oh, sorry, sorry. That was not a good diagram. Come on. Jesus. It's part of my diagram. Oh. Okay, we'll have a shadow will be formed. So let's call this our shadow. This is your opaque object, and this is light wave traveling on this. Now that shows that light, this shows to us that light travels on a straight line. Okay, even if a broad light, now what I just drew was just a point light source, but if we have a broader light source shining on an opaque object, we would still see a shadow will be cast on it. So, okay, I need you to write this. For a single light source, the shadow formed has a uniform intensity. Please write that. For a single or for a point light source, the shadow formed has a uniform intensity. Has a uniform intensity. The shadow formed has a uniform intensity. What do I mean by that? What I mean by that is the shadow will be perfectly, if it is round, it will be perfectly round. But for a broader light source, it would not have a uniform intensity. Rather, for a broad light source, the shadow has two distinct regions. For a broader light source, the shadow has two distinct regions. And what are the two distinct regions? We have umbra, UMBRA, and penumbra. We have the umbra, and we have the penumbra. Penumbra. Okay, that's just the first. We are just the first evidence. Let's go to the second evidence. Number two, formation of eclipse. Formation formation of eclipse. All right. Now, how is eclipse formed? Remember, we have two kinds of eclipse. We have the solar eclipse, we have the lunar eclipse. Now, eclipse is formed when the sun, moon, and earth are collinear. That means the shadow of the moon or the earth is cast on the earth or on the moon. Like I said, we have two types of eclipse. Um, we have the solar eclipse. We also have the lunar eclipse. Now, eclipse of the sun, the solar eclipse. Now, this occur when the sun, moon, and the earth are on a straight line. These occur when the sun, the moon, and the earth are on a straight line such that the moon is between the sun and the earth. Now, the moon is between the sun and the earth, and because of that, it casts a shadow on the earth. The moon is between the sun and the earth, and as a result of that, the shadow of the moon is cast on the earth. And what happens to that? We experience at that moment, we start experiencing an eclipse. Oh God, I should have something that has to explain that very well. I believe, I believe, I believe. Okay, awesome, awesome. All right. I'm just gonna be very fast with these three. Three. Okay, let's just see this. This is quite. This explains. Okay, this is. I believe this explains. Okay, okay. Wow, 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 wow. Okay, this explains it better.
Imagine that you were standing outside in the middle of the day, and all of a sudden it got dark. The darkest part of the moon, the star, moon and Earth align. Imagine that you were standing outside in the middle of the day, and all of a sudden it got dark. The stars came out, the temperature dropped, and night animals started to call.
Hey, look at how this happens. Hello, are you there?
A few minutes later, the sun came out again and everything was back to normal. What happened? You just saw a solar eclipse. Ancient cultures were often frightened by eclipses. They did not understand why the sun became dark. Eclipses were seen as bad omens or predictions of bad luck or disaster. But today we know that eclipses are caused by the normal movement of the sun and the moon. There are actually three types of solar eclipses. First, there is the most widely known type of eclipse, a total solar eclipse. A total solar eclipse occurs when the sun, moon, and earth align in the perfect position, causing the shadow of the moon to fall on a small area of the earth's surface. For people within the umbra, or darkest part of the moon's shadow, the light of the sun appears to vanish completely and the sky becomes as dark as night. The second type of solar eclipse is a partial eclipse. A partial eclipse occurs when the sun, moon, and earth are not perfectly aligned, so that the penumbra, or lighter outer portion of the moon's shadow, falls on the earth. In a partial eclipse, part of the sun's surface appears to have a shadow on it. The third type of solar eclipse is an annular eclipse. During an annular eclipse, the moon is at its farthest distance from Earth, making the shadow that falls on the Earth's surface smaller than usual. Because the moon appears smaller, the shadow cannot block all of the sun, and the eclipse will appear like a dark disk in front of the sun. Solar eclipses can only occur during a new moon, as it is the only phase in the lunar cycle when the moon is aligned correctly between the Earth and the sun. Eclipses do not happen every time there is a new moon, however, because the moon's orbit is tilted compared to the Earth's, and so they only align sometimes instead of every month. Solar eclipses are actually fairly regular astronomical events. Between 2 and 5 solar eclipses occur each year, but total solar eclipses only happen about every year and a half. Because the area from which a total eclipse can be seen is so small, however, the chances of an individual eclipse being visible from where you are is very small. A total solar eclipse in your area might be a once-in-a-lifetime event. It is important to remember that looking directly at the sun can hurt your eyes or even cause blindness, so you should avoid looking at the sun during an eclipse unless you have special eye protection or filters to block out the harmful light. If you don't have these filters, you can still observe the eclipse by making a pinhole camera using materials from around your home. Find out when the next solar eclipse will be visible from your area so that you can prepare to observe this exciting astronomical event.
Okay, I hope you understood that. Hello? Hello?
Yes, sir.
Okay, now we just talked about the solar eclipse, and I believe that was quite explanatory for solar eclipse. Now, the other kind of eclipse um, we've talked about that the sun acts like a broad light source, and parts of the earth to experience darkness. We have the partial eclipse, we have the total eclipse, okay, and we also have the annular eclipse. All right, we also have the lunar eclipse. This is the eclipse of the earth. This is when this this is when Earth, so that the Earth is between the sun and the moon, the shadow of the Earth is cast on the moon. And most times this occurs during the ninth lunar eclipse. This is when the Earth comes in between the sun and the moon. Okay, now we've looked at number one, formation of shadows to show that light travels in a straight line. Number two, we've looked at eclipse. Eclipse, very important. And number three, the pinhole camera. Number three, the pinhole camera. And that's where I'll be stopping for today. Because from the next time we'll be talking about this, we'll be going to the calculation aspect of this topic. Okay, pinhole camera. Now we is now the pinhole camera is actually a rectangular pin with a pin on its surfaces and a film. Now light rays from now let's just round up on pinhole camera. The pinhole camera, one of the things we are going to be looking at the properties of image formed on the pinhole camera. Number one is that one of such properties of the image formed on a pinhole camera, because we know that light rays from an object will pass through the pinhole and form an image of the object on the screen. What are the properties of the image? The images formed on the pinhole camera. Number one, the image is real. Number two, the image is inverted. That means upside down. Number three, the image is diminished. That means it's small. The image is diminished if the distance of the object from the pinhole is greater than the length of the camera. What do I mean? I said if the image will be diminished if the distance of the object is greater than the length of the pinhole camera, the image becomes diminished. But if the distance is smaller than the length of the camera, the image will become magnified. So that's one thing we should know. So when you see a pinhole camera and I think most times they would checkpoint, I mean, IGCSOY would like to draw the pinhole camera and try to illustrate that, okay, it predicts what will be the what will be said about this image. Will it be diminished or will it be magnified? Diminished means that it will be very small. Magnified means it will be very big. So if the distance of the object from the pinhole camera is greater than the length of the camera, the image will be diminished. But if the distance is smaller or if the length of the camera is bigger than the distance, that means the image will become magnified. And number four, okay, I will skip this number four. The next one is, okay, I've said this, that the smaller the size of the pinhole, okay, please write this also. The smaller the size of the pinhole camera, the smaller the size of the pinhole camera, the sharper the image. The smaller the size of the pinhole camera, the smaller the size of the pinhole camera, the sharper the image. Now, if this happens, can you tell me if the size of the pinhole is too big, what will happen to the image?
The dimmer.
Sorry?
The image will be clear.
Yeah, it will be blurry. So if the size of the if the size is too big, what will happen? The image will be blurry. Will be blurry. So that means before we can increase the magnification, to increase the magnification of the image of the pinhole camera, what do we do? if you want to increase the magnification of the image of the pinhole camera um, with all these rules I've given, what do you think we will do to increase the magnification of the image of the pinhole camera?
Um, reduce the size of the pinhole.
Yes, reduce the size. That means move the object very close to the pinhole camera. Move the object very close to the pinhole camera. That just solves the problem. It's all right. We're going to stop here for today. We're going to stop here for today. I would not. We're going to stop here for today, and that's awesome. We've covered over 2 or 3 topics today. That is awesome. Glory to God for that. All right. We've talked about properties of wave, reflection, refraction, and it's been awesome. It's been awesome. Okay. All right. Any question?
No.
Okay. Thank you, Jesus. All right. Have a wonderful day. Um, I'll be expecting the other assignment. So next time
Okay.
we'll be looking at chemistry, right?
Yes.
All right. Have a wonderful time. Yeah. Bye.